So the DAT, which we have here, let's have a look at it first. I move the camera slightly so you see it a bit better. This is what it looks like. It's not so big. You have possibilities to open the instrument like this. We have what is quite obvious. I think it's the video camera here, the lens. On older systems, you have an adjustable lens. This is a modern one, and in this case, it's a fixed lens, so you don't need to do any adjustment on the lens itself. Then we have the light source down here, and it's reflected through a mirror towards the camera. In between here, just here, we have the feed system, which feeds the system through, or the testing material through the instrument. And this is an 1122, which is the model number. And model 1122 means that we use blocks, aluminum blocks like this, where we attach the specimen. So it's not a problem if you have very thin or very brittle material, so you can put it on top of this carrier. Okay, and we have different types of this. So we have one with 10 holes or wells in it, because we don't want to stop the water or the liquid from penetrating through the material if it can. So that's why we don't want to have anything on the backside. We have other ones where you can put in pieces of wood or whatever. We can tailor make any request depending on the customer's need. This one is made for HP. When I make the print head, the inkjet print heads, I put the little, if you take a print head and you look at it, you have the little metal piece at the end of it where the ink actually comes out. This is the hole for that piece so that I can put it in and I could measure on them. So we have a large variety of different block feeds for this 1122 model. The system has, of course, it's possible to change that feed system quite easily. Let's see, we can open this there. And here in my hand now, we have a strip feed, which makes it possible just to cut if you have a board material so that is less than 1 millimeter thick, you can just cut strips and insert it. You don't need to put it on any carrier. You just put in the strip itself, and it will feed through, and it will try to stretch the material as much as possible to get a nice horizontal sample to measure on. It's a little bit more work with this one, and it tends to cause more problems for customers because they might end up getting liquid into it, and then they have problems when it feeds through and you get small pieces stuck in it, etc. So we have more problems with this. And I would say also, if the customer really want to have the top performance of the system, then I would go for the 1122, which is the block feed system, which I have installed here now, since it's more versatile and it's more sturdy. So any questions on that? Okay. So to the strip feed system, we have a calibration tool, which is this one here, and contains of a magnetic pen and 2 steel balls. And the steel ball is measured. We know the diameter of them, it's exactly 2.000 millimeters, and you present that to the system, and you should have the numbers here coming up on the display. Okay? I don't want to do too much I mean, to take out the feed system, it's quite easy though. To do it, you remove the mirror, which you have here. Take it out like that. And then you use an Allen screw, and you have 3 screws, 1, 2, 3, like a V. And by just unscrewing those 3 screws, you can take out the feed system. You still there, guys?
Yes. Yes.
Good. Okay. And when you've done, every time you change the feed system, of course, if you do that often, some customers does, some doesn't, you need to calibrate the system when you put it back in. So we put back the mirror. On the other side of the instrument, here we have the pump, which is a syringe pump. We use standard 1 milliliter syringe, but we replace the rubber plunger with a Teflon plunger. So it's not the one which you could buy in a drugstore, really, because we make this Teflon tip and we replace the rubber one, so we get better precision in the syringe. And at the back here, you have the adjustment knobs for the camera position. So here you set the height of the camera depending on how thick your material is, and the tilt angle depending on the calibration. We will look through that.
Krister?
Yep.
A stupid question you may have answered. Why would you want to remove the feed system?
Well, but it's because, well, for sure, for you know, when you, because it's the system is called 1100. The DAT 1100 is the concept name. And then we have different feed systems. So you can easily replace the feed system with another one because you want to measure something else. Oh, maybe okay. You have, you know, maybe 1120, for example. It's just a shelf. So you take out this automatic feed system here and you put in just a shelf. So you can put in an object if you want to measure on that.
Okay.
Then you have this one, which is 1122. It's the block feed system, which is the most flexible one. And then the strip feed, which I show you, this one, is another feed system. So maybe you only have like copy paper material, and that's the only thing you have, and you're happy with the performance of this, and you don't have too much problem. So then you would use only this maybe. So it's depending on you know, the variety of material that you're running, I would say. And then we have another ones, you know, like 1123, which is a micro precision system for blocks like this, where you want to take very, very small steps in between because you want to put 4 droplets on each little square here, rectangle. And we also have 1124, which is a saturation sensor. That is, when we put the droplet on top of the paper, we start a timer, and we count the time when until we get contact on the back side of the paper. So then we can measure the time it takes for the droplet to be absorbed or pass through the material. Some customers are interested in that. But I can tell you, maybe we sold around 300 units of this around the world, and like 95% of them have the block feed system. So that's the most common one. So that was always recommend that to customers if they don't have very, very specific needs. Yeah.
Krister, with the block system, you can basically you have the possibility of putting in different grades of paper. In other words, right? It's versatile, so you can go from what. Is there some kind of range of grades you cannot do?
On the block feed, you mean? No, not really. I mean, as, you know, because if you have very thick material, that might be a problem if you use the standard blocks, which is this one here. But then we can mill it down, so then your material will still get in there, hopefully. So I would say it's not really any reason not to buy the block feed system.
Okay.
It's a bit more tedious because you need to use the double adhesive tape to hold your specimen on top of it, flat and even, etc. So that's the drawback, but it's not a big thing, really. I don't think so.
Okay.
Okay, and so that's what we had here. Look at the back side. Let's see if we can turn it around. You can see here we have just the power in, the video out, and the RS-232, old thing, but still working. And we use the USB to RS-232 converters if needed. And today you might need it now and then, I think. It's getting harder to find computers with RS-232. Then another thing which is very important, that is, of course, we need to install the image grabber, which is installed into the computer, this board here. So it's a PCI bus, standard PCI bus, not PCI Express or so. So, and this is also a problem because we cannot buy this board any longer. So we have a few in stock, and as soon as we are out of them, we have to sort of change camera inside the system and use another interface. And this is something we already have started, so it's not a big thing really. We will go for a Giga E camera instead. So you will not need this image grabber because it will go over the network connector on the computer. And that's a good thing also because you will then be able to run on a laptop, which today it's impossible. Most of our computer looks like that. It's a typical computer for a DAT today. Okay, any questions on that?
What's the magnification of the camera?
The camera I'm using right now, you mean, or?
Yes. Well, the camera the camera
this one.
in the unit. Yes.
In the unit. Well, we look the field of view is 10 by 7 millimeters, I think it is. So that is what you will see on the screen. Okay.
Okay.
Good. So what I have done here is that I have put in the water. So I have water in the syringe. I have a button here on the side, which I use to adjust the pump position. So now it's in the back position. So if I keep this pressed, it will move forward. As soon as I release it, it will stop. So I can move it to any position. You see, it's not a fast one. It takes a while for it to go from one end to the other. So, and if I want to go all the way back, I click once. It will move all the way back until I press forward, then it will stop. Or I want it to go all the way back and I just leave it like that and go and have a cup of coffee or something like that. Okay? So, now it's in the back position. So you install the syringe, you lock it here with the little screw that holds it in place. We have some different tubing colors. This one is, the syringe tip is red. Let's see if I have the other ones here. That's the most common one for water, I would say. This is the package that comes with the instrument. You have two other ones, one pink, one lilac, and one red. The red is 0.5 millimeters in inner diameter. The lilac is 0.2 millimeters in inner diameter. And the pink one is 0.9 millimeters in inner diameter. And to select the right one, it's depending on the liquid you use. For water, the red one is perfect. For alcohol or other liquids that evaporate fast, I would go for the lilac. For high viscosity liquids, I would like oils, etc. I would go for the pink one. So it's good to know. And then, of course, this is just a sample package. And if you order it after you got the instrument, you buy them in a pack of 5 each. Okay. So the software, let's see, kill it. Looks like this. So this is the computer screen. It's okay. Maybe I should zoom in a bit more. Okay. So this is the icon. So the DAT3 is called. We start it up again. And this is what the interface looks like. Not so very exciting. We can go to setup first to have a look. In setup, you tell the system where you want the data to be stored. You can see here where you're connected to COM1 in this case, if you have more than one COM port on the computer. It also tells you the version of the software, 3913. It also tells you which instrument that's connected and the revision of the EEPROM inside. You can see a live image. So if I now press the drop applicator here, I can see it's live, it's moving. So that's good. So that's basically what you do here. On the liquid, you can add, this is the liquid that we send, or the liquid table that comes along with the instrument. So you have some of them here. If you want to add your own liquids, some special ones, you can do that. You just go for new, etc., and you add one here. That's pretty much straightforward. So water, we can see here, density is 1. It's pretty close anyway. Surface tension, 72.8. That's what it should be. The dispersive part of the surface tension is 21.8, and the polar is 51. That's sort of just the basic numbers that's put into the system. Okay, so it's not much we do here. Just go out, and the first thing we want to do is to make a calibration to make sure the instrument is set up correctly. And for that, yep.
For those calculations, we have to know all that, right? Surface tension, if you're using a liquid other than water.
Yeah, well, you need to have the density, etc. You know, you need to know this, the surface tension. You need to know that of the liquid. And for a pure liquid, it's not a problem. The density, it's also quite easy to look up in books, etc. And the dispersive and polar part might be harder to find, but you need them if you want to use them in calculations. If you only have the surface tension of the liquid, because you don't have the dispersive or polar part. In this case here, we can see that this bromonaphthalene is totally dispersive, totally non-polar. So it's fair numbers. But for some other ones, you will have like formamide, it's 58%, 58 in surface tension, and the dispersive and polar part are you have numbers on both of them. So this data you need to be able to use your new liquids to be calculated with. Did that make any sense? Yeah.
The customer would have to know that, wouldn't he? Depending on
There's
the liquid.
nothing you should know. No, you don't have. You're not a surface science guy.
Yeah, that's what I mean.
If the customer are into that, they should know.
Yeah, exactly.
They don't know, they have to find out.
They have to have that information prior to testing, for sure.
They have to have it, yes, exactly. Nothing, they can't really, I mean, we can't demand of you that you should know it, because I think that's unfair. Okay, so the first thing, as I said, is that we should calibrate the system. And to do that, we have a calibration tool. Skype call. Yeah. So this is the calibration tool for the block feed system. It's made out of a block. Makes sense? So we have 2 steel balls, one that we set the scale factor and the threshold on, and one that we measure on. And this one is pressed into aluminum bar, and it sticks out of 0.924 millimeters above the surface. Okay? So we insert that one here, feeds it into the system, and we press calibrate, and then we have a picture like this. So what I will do now, I will lift up the drop applicator a bit, get it out of the picture, and I want the surface to be at the red lines here. That's my surface marks, okay? Question? No?
No.
Okay, so then I have the two wheels at the side here, one that's called height and tilt that I showed you before. So I just adjust the height, so you see, ends up at that mark. We go both directions, of course, so set it like that. Close the lid. And the system tells me to insert a semi-sphere, but I will not do that. I will just press start. And by pressing start, I will make a new calibration, because this is the validation mode which we are in right now. That is, in this case, instead of calibrating, I could start with just showing this, the semi-sphere. And now the system looks at the semi-sphere, and I have entered the number 924, which was on the block, into the system, so the system knows what it should expect. And if everything is correct, I should get green numbers, and I get green numbers, so I don't really need to calibrate. So this is a validation to make sure that the calibration is okay. I don't need to calibrate. So, but I want to show you a calibration, so I will do it anyway. So I put it in again, and by pressing start, the calibration will start. First, I get a focus bar, and this is leftover from, or for customers that have the zoom, or not the zoom, the adjustable lens systems. But since we have the fixed one now, it's nothing to do. It's preset. You don't need to do that. So the only thing you need to do is press next. So we do that. And the system sets the threshold to 134. And that is where it should draw the line between black and white in a grayscale image. So at grayscale 134 out of 255, we say, okay, so everything that's higher up than this is black, and everything that's white, and the lower none is black. So it's fully automatic. It's nothing you really need to do anything about, but it's good to keep an eye on the number, because it shouldn't vary very much from time to time. And it's all recorded into a log file, an event log file in the system, so you can track it back and see what it used to be or so. So if the lamp would break down or so, this number would go down quite a bit, because then it needs to get more light out of the system than it can deliver. And so you press next, click next when ready, we do that. So now it calculates the scale factor, which is it knows that this diameter of the steel ball is 2 millimeters. So it knows how many pixels it has. So it calculates each pixel, and it comes to an X and Y diameter of 0.014 millimeter. Okay. Next thing to do is to insert a semi-sphere. And then you just press the key here. You have two keys. That's single step, and that's just feed it out. So it's like a tape recorder. Okay. And then you get the numbers, and you have the tolerances here. So for the height, it's plus minus 0.02, and the base and the volume and angle, it's plus minus 1 degree. I can just show you what it looks like now if I adjust the camera wrongly. So I adjust it a bit like this, and see what we end up with. So now you see I have red numbers, which means, well, the system doesn't see this steel ball correctly, because somehow it sees it from above. Since I have a too high number here, it's 0.95 millimeters, it should be 0.92. So it's too high. So when I know that, I know, okay, I need to adjust the camera downwards. And then I always put my finger in here so I can feel which way I move the camera, because now I will move it down, and of course it goes up on the screen, so you will just get confused by looking at the screen. So it's better to feel which way you move the camera. So that now I moved it down, and then I used the tilt wheel, it's the rear wheel, to level it back again on the two lines. And we can see, well, so I'm a bit too low now, because I read 0.91 and it should be 92, so I could lift it up a bit. So I raise it a bit, and I level it back again, and we should be there. Okay? So that's calibrated and everything's fine. We close the lid. So let's run a sample. So we feed this one out, press the key, keep it pressed, pull out the calibration tool and put it back in its storage. Okay? So this system will be shipped out on Monday. We managed to hold it here another day. So this will go to China. Okay. Let's see. Tape. So I take the block I want to use. I want to use this one. I take the double adhesive tape. It's made out of 3M tape. It's like a post-it, you know. And I peel off one of the shield, one of the. Always the one. Thank you. Should be like that. Peel off this one. So there are two different adhesive sides. One that is more sticky, and it's this one, which is not the printed one. So I put that on top of the block. I put it up here so you can see what I do. And I just place it so the holes are aligned with the holes. Then I make sure it's pressed on firmly. And then I pull off this one, and so here it is. And this is like a post-it, so it's not too adhesive. So that means that you can use it many times, the same tape, if you have material that doesn't leave too many fibers on the surface. Then I have a strip. So this is actually from the round robin test. That should be done. So I cut a strip. It's like between 10 to 12 millimeters, I would say, wide to fit here. It can be smaller as well, but or not more narrow. But this is a good size. So I put it on top. I don't touch the surface which I will measure. So I put it on like that, and then
what type of paper is that, Christer?
Well, what?
What type of paper is that? Like a fine paper, or?
Yeah, it's like a copy paper.
Copy paper, okay.
Yeah, something like that. So I put it on, and now I just want to sort of put my finger on it, but I shouldn't do that. So I turn it and press it against the same material. That's what I normally do anyway. So this is the same paper. So I just press it and make sure that it sort of is flat and horizontal and no, not cockled or anything like that. So seems to be okay. Put it in here to the instrument. We are still in the calibration mode, so we go to exit. And then we want to measure contact angle. Well, let's do that. You can put in an operator here. So I put in my name, for example. So, as I've done. So now, yeah. Okay. Do it again. New. Thank you. So now it's my name here. And we go for contact angle. So now we are in the settings of the contact angle measurement, and I click advanced at once, so we have all the settings here now. There's not much really to work with anyway. I mean, it looks a lot, but it's not that. So you tell the system what kind of liquid you have, and we use water. So water. You tell the system the length of the measurement. Right now it's 0.2 minutes, which is 12 seconds. So that's fine. You can change it here. Anything that you change, which will be marked red, and that is because it's not saved in the test profile. The one I have here now is default. Let's do it properly like that. So now I have the default test profile, and this is what it looks like, all the settings. If I change something here now, maybe I say, well, it's only 6 droplets, so then it turns red. I tell it the drop size should be 4 microliters, which is standard one, so I will still keep it going with that. The stroke pulse, which is the force we use on the drop applicator. You still have the picture? Good. That sort of move the drop applicator and makes the droplet go over to the surface. Is this one here, and so we go for something like this. The check times, which is, I will show you, 3 times. Instead of getting the full diagram, which you will get from the system, you could choose to only look at these 3 times instead. So 0.1 second, 1 second, and 10 seconds. Because if you want to transfer the data from the system into LIMS system or so, laboratory system, you don't want to feed it with a diagram. It's better to have a few time stamps. This is time stamps for that. At the end here, we can put in a descriptor. Why not test? That's all you need to do, really. And since this is now a sample which we don't know too much about, just put it in, and this is the first time we will test it. We need to make some adjustments. The first thing I would do is to adjust the surface again, so I'm back on the red lines. And the reason I'm not there right now is because we put the tape on the block and a specimen on top of it, so it adds to the thickness a bit. So, but I have the height wheel, which I can adjust without changing the calibration. So now I've changed it a bit. And you can see here, I have some air inside the tubing. So I will just, okay. So you see, here comes the droplet. So I don't want to use it, so take it out like that. Okay. I can adjust the height of the tubing in the similar way as the PG. So I just release this nut here, and I can pull the tubing up and down to set it to the desired height. I lock it again. Now I can move it. And when it's time for a totally new specimen like this is, we need to sort of set up the stroke pulse correct and the distance for the tubing to the surface, so it sort of works as it should. And if you read the TAPI standard or the ASTM standard, it will tell you what to do, but I will show you. It's just a few steps. So first I will put the system in manual mode, that's 0, which means the system will not do too much if I press fluid now. It will just pump out the droplet. So it's set for 4 microliters. So fine, I pump out the 4 microliters. You can see it there. Then I will manually move it down toward the surface. So I just press this one slightly until I can see it comes in contact. And then I release it slowly. And if the droplet releases from the tubing when it's back again at the starting height, then the distance is okay. Because if it will still be standing in between here, the contact angle would be very low on the surface. This is, sorry, I will take that one back. The surface free energy is very low, so the contact angle will be very high. And if you have a very high contact angle, it means that the liquid are not really interested in to go over to the surface. It rather sticks to the tubing. So in that case, you might have to increase the distance, the tubing between the surface and the tubing for it to be released. So this is a little bit wider now than it normally would be because the contact angle is about 100 degrees. Okay, so now we found out that the distance seems to be okay. We move to a new position. We pump out a new droplet. And now we want to set the force we use to get the droplet to go over to the surface. And then we have this key here called drop. It's set to 6.4 now. So I will lower that force to something and we see what happens. See, it shakes, but it didn't get in contact with the surface. So I need more force, okay? So I increase, and this number you see here is actually the length in milliseconds of the electric pulse that we send out. So 5.7. See, it moved over, but still, it needs a bit more to actually go all the way. So let's go for 6. Seems to be okay. And this pulse we use should be as gentle as possible. Because if I set it to maximum, of course, I will always put the droplet down, but then I will sort of press it down to the material and I would read a much lower contact angle than it actually has. So let's try again. We pump out the liquid and we press drop. Looks fine. So now we set up the system for this material. If it had been another material, which I will show you in a few minutes when we turn it around, it will have another contact angle. So we close the lid. We go to exit, and we tell the system that, well, we used application mode 0 now, which was the manual one. If I go to application mode 1, then it means when I press start or measure, the system will automatically pump out the liquid. It will put it down to the surface, and it will start the measurement as well. In mode 0, the only thing the system do is it activates the drop applicator and it starts to measure. Mode 1, it pumps first and then it moves the drop applicator and it measures. In mode 2, it first feeds the sample, then it pumps out the liquid, and the last thing it does is put down the droplet and it measures. So this is the most common one that you use mode 2. So we have the stroke pulse is set to 6.4. We have asked for, let's go for 4 droplets and just 0.1 at 6 seconds. And we change the time here for 5 then, a test. We are set for a test now. We go for measure. Yep, shoot.
Now that you've set up a specific procedure for this sample, do you save it and say, okay, the next time I do it, obviously I don't have to go through all this?
Smart guy. You see, I can press this one, save as. So we call this TMI test. And we save it. So everything becomes white. All the red lines are gone, and I have my test profile is called TMI test. So by choosing this, when I enter here, I have all my settings as it should be for that specific material. Okay, so let's see what happens. I press start, the system feeds it, and this is the first one. Okay, let's see what happens. Took a while. That's a lot of thinking there, I think. Okay. So let's take another one, just to see what it looks like. If it looks the same or not. Okay, so the first one, I don't like that one, so I would like to redo it. take it away. Never trust the first droplet, I used to say. But okay, so now I have 2 droplets. And you see, this is the first droplet in the sequence. And this is the next one. And if I continue to put down droplets, I will have more. Okay, let's do that. We can do that. So we have done. So now the system will continue automatically until we have 4 drops. So now 1, 2, this is the third one. And then we should have the 4th one after this one. It's quite rapid. When you set it up, it's quite easy to run the tests. And the system will create a lot of data. At the top here, you have the 3 check times, 0.1, 1 second, and 5 seconds. You have the contact angle and the volume for each time. You have the average, of course, which is the interesting number, and you have the variation. So a low variation would tell you that the system is homogeneous. It's a well-treated surface. And if you have high variation, could be many reasons for that. It could be because it's you have some dirt on also. Okay, so now we can compare the 4 different droplets, and this is the most crucial thing, or the most important thing with the system. That is the timing which we have in the system. What you see in front of you here is 4 different droplets. Show you the droplets. Here you have the drops. See, neat and nice, placed on the material. So the first picture on the first drop is this one. The time is 0, as we call it. The next picture at 20 milliseconds, we should have the droplet on the surface. It should not be in contact with the tubing any longer, as it is on the first picture. The image here should look like avocado or pear, something like we see right now. And then I take the next droplet and I test that one, and it looks the same. And the next one, and the next one. This is something our competitors hasn't achieved yet, because they can't synchronize. They don't have this synchronization. And when you read the TAPI standard or the ASTM standard, you realize that you need a synchronization to comply with the standards. So that's why we are the only one that do that at the time, at least. And the precision we have in the system is ±1 millisecond. So I can actually adjust this droplet so I could have it by just changing one of the parameters. I can get it to be taken, the first picture to be taken a little bit earlier, so I have more of contact here with the tubing. I have another one there. Yeah, I have 2 more. Let's see. So this is, remember this picture here, what it looks like. So we say it's exit without saving. And then I have this parameter here, which is called travel time. That is the time it takes for the droplet, depending on the distance to the surface, to get to the surface. So if I change the travel time to maybe like 2 milliseconds earlier, let's see, I should move to the right position and put myself there. I think I do it like that, and I do some tricks here, and I go for measure, and we have it here. No, not any longer. And we go for start and see what this looks like. This is now 2 milliseconds earlier than the picture before that you saw. You see, now it looks more like a pear, maybe. So now I change the timing 2 milliseconds. It's not much, but it's enough to makes a difference. So maybe this is a better setting, I would say, for this material. So I jump out again and I save this travel time. I want it to be mode 2, and I say save. So now this is saved on the TMI test. So let's run full strip then. So I take my specimen. Yep.
Kristen, do we have a cutter for those strips?
No, it's just a standard cutter. No, nothing special. Not really. I have one over here, you know. You've probably seen it. I didn't use the paper there. But that's the one at the end there. That's the one I use.
Okay.
So that's what you need.
Okay.
Okay, you all get seasick now. Okay, okay. That's it. Okay, so I put my new specimen on top here. I'm happy with that. I put it in, and everything is set. We just go for measure. Since I didn't say before, I will not have a problem with that. What I do normally when I measure is the first droplet I want to see. So I press start, and then it puts down it on the surface, and I look at the first image to see that it looks okay. And so we have the pair, and the next one, it's released. If that looks okay, I say new drop and continue automatic. And I just let it fill up the batch. Now it's only 4 droplets, but that's okay. So it's quite nice and easy to run. As soon as you find the settings, it's nothing much to do. I mean, you put in the sample and press start. And then it's a matter of taking care of the data.
Hey, Krister.
Yeah. Hello?
This is Mike Salucci. How are you?
Hi, Mike. Yeah.
I have a question for you. How
Sure.
does this system, the DAT, does it find the baseline easier than the PGX? When working with something like like a textile. You know, I did some work over at WL Gore with the PGX, and we had a really hard time. So they come to mind now after I've seen the DAT as a potential.
Yeah.
You know,
Okay. I can tell you. Yeah. Yep.
Just one more question, Krister.
That should. Okay.
Yeah, just the distance of the top of the specimen to no, off to the right by where it mounts, the loading specimen, where the specimen loads on the side of the DAT. There you go. What's the distance from the top of that sample up? I mean, how much room do we have to work with varying thicknesses?
Okay. Well, I would say you have around, without doing anything, I think you have around 2 millimeters.
2 millimeters?
Of course, yeah, 2 millimeters. If you have thicker materials, then I suggest that we mill down. The holder, then you can get it thicker.
Okay.
Yeah. I think you can go into this is like 6 millimeters thick, so maybe you can get in something like 8 millimeters.
Gotcha. Now, one of the things we had a problem with was with the PGX was every time we turned the PGX in a different direction, it was looking at the grain of the textile, the weave of the textile. Yeah. And it really had a hard time. Every time we tried to set up and change certain things of the image, it just had a really hard time finding the baseline. So it just made it really
imagine
difficult.
That. And I can tell you why, and why it's so much easier with the DAT. Because the DAT looks at the material horizontal. So we just look at the horizon of this surface here. And like this, so we have it exactly horizontal. So the only thing that you see sticks out or up above the surface, that is the droplet. But in the PGX case, you look a bit from above with an angle on the surface because you cannot put the camera under the specimen because that's the table or it's just not possible, physically possible. So that's why you need to look at the material from an angle. I think it's around 3 degrees angle, and that makes it a little bit or much more sensible to any variation on on the substrate or in respect of lighting conditions. And sometimes you manage to set it right, the threshold or the camera setting for the PGX, and sometimes you need to adjust it a while until you find it. So it's much more sensible to that than the DAT. The DAT is pretty much more straightforward, but of course it has the drawback that you need to cut your specimen and put it into the machine. And if you can't do it, you can't do it. Then you have to stick to the PGX.
Correct. Okay.
Yep. So that's the reason.
Okay. Now, as far as advancing and receding is concerned, I mean, is it easier to do advanced?
Well, it's not so much. Well, it's a bit easier because we don't use. The only thing we do, here is that we use a tilt table instead. So that is, we put the whole unit, the whole instrument, on top of a tilting table that will actually tilt the instrument just like this, slowly, and then back again. So what will happen then is that the two angles you have on left and right side of the droplet will, of course, depending on how much you lean the instrument, will be different. And one is then the advancing, and the other one is the receding angle. So if I do it like that, the advancing will be facing downwards, and the receding will be the one upwards here. That's a bit different compared to what you do with the PGX, where you sort of pump out the liquid and you fill the droplet, you sort of add water into it until it snaps out, and then you suck it back again in the syringe. And we always told customers that the DAT does not really make it possible to get the contamination because you will not contaminate your liquid since you're not sucking it back again into the syringe. That is what you do with the PGX in one respect, because when you put out the liquid, you get it attached to the surface. Might be something that you dissolve on the surface, and then you put it back into the syringe. Might affect your liquid. Okay?
Yep, sounds good. And how about static versus dynamic? Can we do both on here? I can see you doing dynamic.
No,
can we do?
You cannot. No, you only do dynamic here. So when I've now made my measurement, I can go to. I have a key here that's called graph, and this is what I have. So I have all my pictures. Each picture represented by a red dot. The yellow dots are the check times. Okay. So we have 0.1, 1, and 5 seconds. And this is a logarithmic time scale. So this is the last droplet. So if I press this one, you see it shifts a bit. And if I go for batch, I get the red line, which is the average, this one. Then I can see if I have any outliers. Maybe I'm more interested into the volume and to see what it looks like.
So how do we calculate surface energy then? Can we calculate surface energy on here for the ASTM standard, or does the customer has to do that on their own based on one of the data points?
I would say that they should do it on their own, because here we can
do it on their own.
Yeah, we can do it here as well, but I will show you. But okay, for the time being, so this is what you can do. You can also, of course, if for some reason this picture was wrong, you can take it out. Delete this entry or delete this entry, and all below you can do that. So I only take that one out. So and one dot will be missing here. It's a dot missing here now. So it's and you have the calculation here, the CV, the coefficient of variation. And if I sort of maybe you detect an outlier, immediately as soon as you untick it here, it will be recalculating the average here, so we will see the effect at once. Maybe you want to add another droplet because, well, I need another one. So you just press extend batch and start. So you have another drop. You can run 10 droplets on the block. That's the maximum length which we have. But I think we could. I mean, if customers say, well, we won't buy one if you can't buy, or if we can't run like 15 droplets. Well, I think we can make a block that can take 15 droplets also, so it shouldn't be a problem. So now I have 5 measurements here, you see, so 5 tabs, and I'm happy with this, so I go for save, and I say save and exit. So now it's saved. Let me just show you what happens. So this, now we've tested this side of the paper. If I now turn this paper upside down and run the other side, let's see. And I don't change anything, just because I'm a bit lazy. So I just put it in here. I have the same settings. We call this test 2. And we go for measure, same settings, and we say start. So here it comes. It's a bit different. And then we say, well, new drop and continue automatic, because I want my batch to contain at least 4 droplets. Normally I would go for 8 droplets in each batch. That's more a sort of statistically safe value. Of course, the more you run, the better it is, but you have to stop somewhere. So 8 is a good number. So now we have 3 droplets, and this is the 4th.
And Krister?
Yep.
I've sort of been in and out of the office. Has it been mentioned that this is the only machine in existence that will meet the TAPI standard?
Well, we try to say it, you know. But our we used to put a sticker on our leaflets, but yeah.
Right, but I'm saying in this webinar.
Yeah, I already said it.
You guys attending, did you?
Yeah, I think I said it.
Did you realize that this is the only machine in existence that meets the TAPI standard?
To my knowledge, I might add, but yep.
Because of the time dating.
Exactly. Plus minus 1 millisecond, and we can control the timing. We can control when we start to measure, and each droplet will look the same. That's what you see here. This is different droplets.
Point to where the time is, Krister, so that
the time is here. Yeah. This is 0 millisecond, and at 20 milliseconds for that drop, it's released. So if we compare the 4 droplets, the first picture looks pretty much the same. And this is water, which we put down on the surface. I think it's good.
Yeah, and I'll also mention that in the cigarette paper or cigarette manufacturing areas, it is the only machine that is going to be able to give them the information they need. Because of the quick throughput of cigarettes through the machine and the adhesive they use to seal the cigarettes.
Yeah, it's true. It's true. So it's quite a good piece of equipment, I think. So we save this one now. So now we have 2 measurements. We have the test 2 and the test. We're happy with this. We don't do anything more. So let's go to the view software where you sort of look at the data. The 2 last one here is what we have been looking at. We can compare them. We look at the angle. So we get the possibility to write something here. And we go for OK. So, and then we have it like this. So this is what it looks like. So we have the two samples which we tested. One contact angle was up here, and the other one was down here. So big difference for sure on the 2 sides of this same material. So, and if we would like to calculate surface free energy, I heard that, then we need to have 2 specimens, with 2 different liquids, of course. One with water and one with non-polar liquid. So, if I go here now, first I select the specimens which I have of interest, of course, which I want to calculate the surface free energy for. Then I press SFE, and for these 2 samples, of course, I've been using water for both of them, but just to show you, I would trick the system, and I would tell the system this was diodmethane, for example. So now I have this first, the test, and with the test 2. So we press calculate, calculates the surface free energy out from the two measurements which we have done. And then if I press report, I can get a report like this. And I get the total surface free energy, and of course it changes over time. So when should I take the number? I don't know. It's up to the customer because it's a dynamic process. It's hard to say when they should take it really. And then you have the dispersive diagram and the polar diagram. And then you have all the numbers underneath there. But this system only, the DAT only calculates for the surface free energy with 2 liquids. The PGX can make it with 3 liquids, as you know. So then you would also get the polar and acid part of the surface free energy for the substantial. Okay. And of course you can compare more, etc. here. So you get a lot of them. So it's quite easy to put them together and make get the diagrams out to have something to look at. And it's still standard text files, so it's very easy to open it in Excel, for example, if that's needed. What else can you do with the system? Well, you can measure surface tension. So if you go here, you pull this one out, put in another block like this, and we just raise the tubing a bit. So this is mainly to make sure I use pure liquid and that I don't have any contaminated liquid. So I choose the number of drops, maybe 4. Droplet size, well, 11 microliters should do fine. Pump today, we don't need that. And it's water, and we say measure. See what happens. The tip was a little bit bent there, so maybe I should cut it, but I don't think it's that necessary. So now it pumps it out and it measures on it, and it's 72.6, which is quite okay. So it measures the dimensions, as you see with the lines on the screen. It's the same way that the PGX does it. So. Of course, it should be stable. It shouldn't be too shaky. So. And this is the last one. So, there you have it. The average was 72.6. Quite quick. You can save it, you can print it out. Maybe you would like to take, this was an out, I don't like that, so I take that one out. Poof, it's gone, and you have the average, it's affected immediately. Takes it without saving. So, well, that is, I would say, a quick overview of the system. Questions?
The customer, that tobacco customer in China, I don't remember the details, but do they know how to operate this unit?
I don't think so. I don't know.
That's interesting.
Yeah, it's interesting. I hope. I mean, I think it's Max Lieu. You know, you met him.
Yeah, no, I didn't meet him. I'm going to meet him in March.
Louis? Yeah. This particular unit for China, this is the one going to China, right? For Max?
It will go out on Monday morning.
Yeah, for Max, right?
Yeah, for Max.
Anyway, it doesn't matter. I don't believe it's going to the tobacco industry. I believe that particular one is going to a university.
University, that's right. It's university in Szechuan, was it?
That's exactly right.
Yeah. Okay. That's right. Okay.
And yeah. So.
Yeah.
That brings up a good point, guys. What do we do with you know, you sell one of these for setup and training? You know, I don't. You've given a great presentation, but I mean, even just looking at the screen, there's no way that I'm going to be able to go through this with a customer.
No, but I think, I mean, the first unit, maybe we could install it together, you know, and then you're on your own, so to speak. Because before we go to the customer, we could make in Delaware or so or somewhere else, we could sort of train on it and get to work a bit with it. Or you come here. That's also okay.
Yeah, because I think we're going to get in over our heads if we start going to universities with this.
Yeah, maybe. Yeah.
Kevin?
Yeah.
Tricky.
The reality is that this is not a difficult machine to operate. Okay, although a member of the A team, was able to operate this thing without any difficulties.
Yeah. There is a help file.
I'm more concerned about being able to explain each and every box because the way the way this is run down.
But then you press F1. F1. No, it doesn't work any longer. No. Microsoft took it away.
Here, guys. Here's a suggestion. This is going to university, and I doubt it very much if David has been trained on this.
No, he hasn't. Jason was, but then again.
Yeah, but Jason's no longer there. No, but what I'm saying is, this video can help. This is the reason why we're videotaping this.
Mm-hmm. Yeah, it might be.
By the way, if you guys don't know, we're videotaping this, so all you guys are going to get a copy.
Yeah. I think I could stop the video recording now, could I?
Yes, you could. Yes.
I do that. Are you sure you want to? Yes. Stop recording.